Welcome back to Decentralized Application Development Crashcasts. I'm Sheila, and if you're enjoying our deep dives into the world of decentralized systems, please take a moment to rate our podcast on your listening platform. It really helps us reach more developers like you. Today, we're wrapping up Chapter 3 on distributed hash tables with a crucial topic: fault tolerance and scalability in DHTs. Victor, are you ready to make our listeners' heads spin with some resilient, scalable goodness?
Absolutely, Sheila. I'm excited to dive into this topic. It's where DHTs really shine in real-world applications. But before we get into the nitty-gritty, why don't we start with a quiz to get our listeners' gears turning?
Great idea. Listeners, here's your quiz question. In a DHT system, what's typically considered a safe replication factor to ensure fault tolerance? Is it 2, 3, or 5? Think about it, and we'll reveal the answer at the end of the episode. Victor, any thoughts on this question without giving away the answer?
It's an interesting question, Sheila. It really makes you think about the trade-offs between reliability and resource usage. Too low, and you risk data loss. Too high, and you're wasting storage and bandwidth. I'm curious to see what our listeners think.
Absolutely. Now, before we dive in, let's quickly define some key terms. Victor, could you explain what we mean by fault tolerance and scalability in the context of DHTs?
Certainly. Fault tolerance in DHTs refers to the system's ability to continue functioning correctly, even when some nodes fail or leave the network. Scalability, on the other hand, is about the DHT's capacity to handle growth, whether it's in terms of the number of nodes, the amount of data, or the number of requests, without a significant drop in performance. These two concepts are crucial for building robust, real-world DHT systems.
Thanks, Victor. Now, let's start with fault tolerance. How do DHTs ensure that data remains accessible even when nodes fail?
Great question, Sheila. The primary mechanism for fault tolerance in DHTs is data replication. Instead of storing each key value pair on just one node, DHTs typically replicate the data across multiple nodes. This is where the concept of a replication factor comes in. It's the number of copies of each piece of data stored in the system.
I see. So if we have a replication factor of 3, does that mean each piece of data is stored on 3 different nodes?
Exactly, and these nodes are typically chosen based on their position in the DHT's key space. The key space is essentially the range of possible keys in the system. For example, in Chord, a popular DHT protocol, data might be replicated to the next 2 successor nodes in the ring.
That makes sense. But wouldn't this replication increase the storage requirements and potentially slow down the system?
Good point, Sheila. There is indeed a trade-off. More replication means better fault tolerance, but also increased storage and bandwidth usage. It's all about finding the right balance for your specific use case.
I can see how that would be challenging. Now that we've covered fault tolerance, let's move on to scalability. How do DHTs handle growth?
DHTs are designed to be inherently scalable thanks to their distributed nature. As new nodes join the network, they take on a portion of the key space, naturally distributing the load. One key technique used here is consistent hashing.
Consistent hashing. That sounds intriguing. Could you elaborate on that?
Sure. Consistent hashing is a technique that minimizes the amount of data that needs to be moved when nodes join or leave the network. It maps both nodes and data to the same key space, typically visualized as a ring. When a node joins or leaves, only a small fraction of the keys need to be remapped, making the process much more efficient.
That's fascinating. It's like the DHT is automatically load balancing itself. Are there any other techniques used for scalability?
Absolutely. Another important concept is the use of virtual nodes. Instead of each physical node being responsible for a single point in the key space, it can be assigned multiple virtual nodes spread around the key space. This helps to evenly distribute the load, even if physical nodes have different capacities.
I'm starting to see how all these mechanisms work together. It's like a self-organizing, self-healing system. But surely there must be some challenges or limitations.
You're right, Sheila. One of the biggest challenges is dealing with churn, the continuous process of nodes joining and leaving the network. High churn rates can lead to increased network traffic for maintenance operations and temporary inconsistencies in routing.
That sounds tricky. How do DHTs handle this churn?
There are several strategies. One is to use stabilization protocols that periodically check and update routing tables. Another is to employ lazy update mechanisms that only propagate changes when necessary. Some DHTs also use predictive algorithms to anticipate churn and preemptively adjust.
Fascinating. It's like the DHT is constantly adapting to changes in its environment. You know, it reminds me of a resilient library system. Imagine if libraries could instantly replicate popular books and redistribute them based on demand, all while handling librarians coming and going seamlessly.
That's a great analogy, Sheila. And just like how a good library system makes finding and borrowing books easy for readers, a well-designed DHT makes storing and retrieving data efficient for applications, even as the network changes.
Before we wrap up, any best practices or tips for developers working with DHTs in terms of fault tolerance and scalability?
Absolutely. First, always consider your replication factor carefully based on your reliability needs and resource constraints. Second, implement proper failure detection mechanisms to quickly identify and handle node failures. And third, design your data model with partitioning in mind to enable easy scaling.
Great advice, Victor. Now, I think it's time to reveal the answer to our quiz question. What's typically considered a safe replication factor in DHTs?
The most common answer is 3. A replication factor of 3 provides a good balance between fault tolerance and resource usage. It ensures that data remains available even if one node fails, while the third copy acts as a tiebreaker in case of inconsistencies.
Thank you, Victor. To summarize today's episode, DHTs achieve fault tolerance primarily through data replication, with the replication factor being a crucial parameter. Scalability is achieved through techniques like consistent hashing and virtual nodes, which help distribute load evenly as the network grows. However, challenges like churn require ongoing management and smart design choices.
Exactly, Sheila. DHTs are powerful tools for building resilient, scalable distributed systems, but they require careful consideration of these factors to work effectively in real-world scenarios.
That wraps up our episode on fault tolerance and scalability in DHTs, and with it, our chapter on distributed hash tables. Next time, we'll be moving on to Chapter 4, Decentralized Storage Systems. If you found this series helpful, please visit crashcasts.com, join our Discord community, or support us on Patreon. Your engagement helps us create more content to demystify the world of decentralized systems. Until next time, keep coding and stay decentralized.